Good afternoon, everyone, and welcome to yet another edition of VIGNYANA KATHEGALU. So today we have Professor Mahesh Anand with us. Mahesh Anand is a professor of planetary science and exploration at the Open University, UK. He was born and brought up in Varanasi, India. He received his BSc and MSc degrees from the BHU and IIT Bombay, respectively. He secured a prestigious scholarship which enabled him to undertake a PhD from University of Cambridge, UK. Afterwards, he worked as a postdoc at the University of Tennessee, USA, and the Natural History Museum, before joining the Open University in 2005 as an academic staff member. Mahesh's research work has spanned geological studies of ancient igneous terrains on Earth, to diamonds, to lunar, Martian, and other meteoritic samples. His recent research has focused on understanding the history of volatiles in lunar samples, especially the abundance, distribution, and sources of water in the lunar interior, something that he would probably discuss in his talk today. Mahesh has supervised over 30 PhD students and postdocs and has published over 120 research papers in journals of high scientific standing. His other research interests include the application of scientific knowledge derived from fundamental research to inform planetary exploration programs and inspire the next generation through knowledge exchange activities. Among many services to the community, he served as a vice president 2019 to 2021 of the Royal Astronomical Society and has chaired the UK node of the NASA Solar System Exploration Research Virtual Institute since its inception in 2009, comprising over 100 members from 15 UK higher educational institutions. And today he's going to talk about water on the moon and its renaissance in lunar exploration. So with that, I invite Professor Anand to please come and deliver the talk.
Thank you very much. Shall I stand there behind the lectern, or is it okay here? Okay. Is it okay? I'll just use that. So thank you very much for the invitation and for the kind introduction, and thanks to my colleague Shama that I'm here. It's amazing to be here with you all, and I was just sharing with two of our colleagues here a coincidence in my life. It seems like the image of Sir C.V. Raman is always there to inspire me from time to time. The very first thing I ever won in my life was at intermediate. I won a competition in our school that was named after Sir C.V. Raman, and that inspired me to do science and follow science. And then in 1997, I got an opportunity to come to RRI and join a workshop that was delivered by a very famous professor from Cambridge, Professor Dan Mackenzie, one of the persons given the credit for inventing the theory of plate tectonics. At that time, I was just a messy student, and again, it inspired me to follow my dreams. And here I am again today. So again, this will, I'm sure it has already inspired me and is going to inspire me further. And as you heard, one of the things that I'm very passionate about is actually sharing the knowledge that I have been so fortunate to gather over the years through so many happenstances with as many people as possible, anytime. And moon is one such object that fascinates me, and I'm sure it fascinates many of you. And we can use the moon to actually engage the wider sector of the society for inspiring people for a variety of things, not just science, but something that everybody can do with the talents they have. So what I'm going to share with you today is a little bit of almost like my life journey. But before I do that, some of you may be wondering, what is this Open University, as you might not have heard the name, or you might have heard Open University, but you may think about it differently. Today, the Open University is going to be presented in the context of research. And from the research point of view, the Open University is like any other traditional university. It is one of such universities in the UK, known for its research, particularly in planetary sciences. It has a very high standing. And we are very proud at the OU. We only have a 55 years history. So it was founded in the year close to 1969. And I say three things happened in 1969. I'm sure the first one you all know, that Neil Armstrong and Buzz Aldrin landed on the moon. And the second thing was that a very famous meteorite called Murchison that actually kick-started almost the latest era of meteoritic science. And then the third thing I say is the establishment of the Open University. Yeah? And since its inception, we have been involved in many of the space missions, primarily led by the European Space Agency, because UK is part of ESA. But not just ESA, we also routinely work with NASA. We have had projects with ISRO. We are continuing with that association. And we also work with JAXA and many other partners around the world. What we specialize in is two things. One is that we miniaturize and build payloads. So again, you must be familiar with that. And the challenge there is to actually miniaturize laboratory scale instruments into something that actually is low mass and high fidelity that can be launched into space. And that requires a lot of engineering and technical innovation, which is what some of the smarter colleagues, they do. And here you see Simeon Barber wearing the same T-shirt that I'm wearing. And that is a T-shirt that one of my students designed for the moon. And we call our project Living on the Moon. Not that we want to go and live there tomorrow, but it is to encompass the philosophy of why we are exploring the moon. And hopefully it will become clearer towards the end that maybe there is some merit in calling that project Living on the Moon. Some of the flagship projects in which we have been involved with is one of European Space Agency's project to go to Comet called 67P, where a Rosetta mission had an orbiter and a lander called Philae lander. Cassini-Huygens, that's an ESA-NASA mission, which had a payload built. So both of them had payload built at the OU. One of the payloads were built at the OU. Huygens was a lander that landed on Saturn's moon Titan, which has a surface science package, some of which was developed at the OU. And we are very heavily involved into a project led by European Space Agency called ExoMars. Let's get back to the moon. It's not very far. And the good thing is that you ask anybody, they will be able to tell you where the moon is. That's not true with any other celestial object other than the sun, of course. Yeah? It's not easy to see things with naked eye. So this is what I mean by moon is the best engagement object there in the sky, with which you start astronomy and then you take people deep into the universe and cosmos, and wherever your interest takes you. And it's not that far. You know that it has been visited at least 6 times by 3 men each time, so that ought to change. Yeah? So, and it will hopefully soon change with the arrival of the Artemis era. So whether through Artemis mission or through some other space agency, I'm sure there will be more diversity being reflected in next humans landing on the moon. And I would like to see moon as an enabler of wider exploration of other solar system destinations. So moon is probably the first place. It should probably take out probably, I think, in my view, it is going to be the place where humans will go after Earth. Right? And that will provide us with a test bed if we want to go beyond the moon. There are a lot of things we still need to learn to survive in space. And one of those things is to be sustainable, to be a responsible citizen. We are not very responsible citizens of the world today, but I think space is a very harsh place. So whether you like it or not, you will be forced to be responsible because you need to have sustainability. And that's where the in situ resource utilization aspect comes in. And so science that we are doing today is actually informing some of those planning for using the resources in situ when you are there on the moon. Of course, for humans, but even if humans are not involved, for robotic things, you still need to explore and utilize the resources that are there on the moon. And I'll show you some examples of that. I mentioned human landings on the moon, and you can see those 6 places where there are footprints still probably preserved today, because moon doesn't have any atmosphere and things don't get lost that easily until there is an impact or until there is another lander nearby trying to land, and then it blasts all the footprints away. The good thing was that when humans went to the moon, they also had to come back. And they were coming back to pick up a few kilograms of rock was not a big deal. So they brought some samples back. But those samples have turned out to be more than gold dust, because they have allowed scientists like me to discover and rediscover things. Yeah, things that were looked at as soon as the samples came back. But 50 years on, when people were re-looking at some of those same samples with the advanced technologies, they were actually discovering things that they couldn't discover 50 years ago, or they overlooked. So this is the importance of samples. And I can't tell you how excited I am to hear about the plan for India to return samples to Chandrayaan-4 mission. And I bet that once those samples are back, they are going to serve the Indian community and the international community for the next 50 years easily. The other thing that you notice in this image is the two sides of the moon. So one is the near side, as it's known, which is what we see every day, or whenever moon is visible. And the other side is the far side. Sometimes people refer to it as a dark side, because again, people sometimes want to use moon in folklore and lots of other creative ways to get people's attention, but there's nothing called the dark side. It should just be called far side, because it receives the equal amount of sunlight as the near side. The main thing is that there is a difference in how the near side appears compared to the far side, and those dark patches are those basalts, those flat lava flows where the Apollo landings happened, where the samples were returned, whereas the far side is much lighter in color and also looks much more cratered. All these round features, they are all craters. They are formed by impactors hitting the moon since its birth, which is almost 4.5 billion years ago. Now, recently, there have been 2 missions. Oops. Okay, it will come later. But, China has successfully landed on the far side of the moon, and not only landed, it has actually recently returned samples from the far side. So that has been probably the most exciting development in the past couple of years, a return of new samples. So China has returned samples from the near side through Chang'e 5 mission, and now from the far side earlier in the June. And the initial results were only published last week in journal Nature and Science, and more will follow. Now, the same dichotomy that you saw in the previous image is seen here when you look at the false color map by showing the topography. So here, anything that's in blue is essentially a lowland, it's a low-lying area, and you can see the scale there. So that's your sea level, so to speak, and then -6 kilometer, and then +7 kilometers. So the total relief on the moon is 1.5 times the height of the Mount Everest. Right? So it's not an easy place to traverse or to explore. So the other thing you see is that there is this feature here, which is much more prominent in topographic map. It's called South Pole Aitken Basin, because its rim extends from the south pole, near the south pole of the moon, to the rim of the Aitken Basin further up north, and it's 2,500 kilometer hole, which is more than 7 kilometers deep in the south polar region of the moon, and it is thought to be the oldest feature, the oldest impact feature on the lunar surface. The exact age is not yet established. In fact, that's why there are many mission proposals to go to South Pole Aitken Basin and bring sample back. But at the moment, the estimate is that it's more than 4.3 billion years old. Moving on, so yeah, so this was the slide that I was expecting earlier. So these are the, oh, yes.
Sorry, very basic question. What was the age of 4.3 billion years based on?
So a lot of samples were brought back from the Apollo missions. They were radiometrically dated here in terrestrial laboratories. And they provided the ground truth to actually age date the surfaces from where they were collected. Based on that, there was a cratering curve that was actually established. Then, counting the number of craters that are there in the South Pole Aitken Basin area, the age was actually estimated that it should be around 4.3 or higher than 4.3. There is no direct dating of South Pole Aitken Basin material yet. Does that help?
Yeah, thanks.
So, yeah, so please, raise your hand and ask questions. I really like the interaction rather than me just talking. So these two places are the Chang'e 4 and Chang'e 6, yeah. So this is Chang'e 4 lander, and this is the Chang'e 6 sample return where it has happened recently. And near side has been obviously quite popular, and of course, India very successfully landed Chandrayaan 3 on 23rd of August last year. Yeah, an amazing accomplishment. On the right-hand side, you see a picture of those 3 astronauts who went on Apollo 17 mission. And you can see the Saturn V in the background. And even today, you can visit places like Houston and Kennedy Space Center, where you can see a model of Saturn V. And I have only been to Houston. I've not been to Kennedy, but Houston is actually laying on its side. And it's enormous. You know, it's almost 100 meters long. And when you stand next to it, it really gives you goosebumps. And you think, wow, you know, when that rocket would have left, how people would have felt who were actually watching live rocket launch. But of course, Harrison Schmitt was the only geologist who actually visited the moon. And a geologist has a very important role to play, because the rest of the astronauts, even though they were not geologists by training, most of them were fighter pilots, because they had to, you know, manage the spacecraft from landing out. They were actually trained in geology before they left. And any astronaut who is going to Moon or Mars, they have to be trained in fieldwork, they have to be trained in geology. But Harrison Schmitt was a trained geologist, so actually he managed to achieve much more than many other astronauts in actually deciphering some of the local geological information from where rocks were collected. And he's still active today. When we go to conferences, he shows up, he presents his talk in the same 10-minute slot like everybody else, right? And it's always nice to hear when somebody comes to you and says, so you're analyzing the rock I collected, tell me more about it. You know? It's nice to actually feel that, yeah, it was all real. And you have the person who actually walked on the moon those years ago. So, you know, some of these things will be very obvious to many of you. In 1960s, it was a space race. So the primary objective was to land humans on the moon, and of course, bring them successfully back. That was the primary objective. Science was secondary. But once you are there, of course, you will be doing some science. And increasingly, as you moved on from Apollo 11 towards Apollo 17, science took more of a prominence, because by that time, it was decided that, okay, the race is over, the United States has won, and then several other Apollo missions that were lined up were actually canceled, because the interest in US public for continuing lunar exploration waned. And so the US government could not justify it, yeah? So nobody goes there just for science. That's the first thing, that it is always driven by one competition or the other. So let's be realistic and honest about it. Nothing wrong with that. The point is that while you are actually competing for something else, what else meaningful thing you can do? And in this case, my argument would be advance the science while that sort of competition is going on. So right now we are there today where India is obviously competing with China and the other space powers. And that is what is going to drive our ambition to go to the moon. But some of us who are not directly involved in those political discussions are mere scientists. We can still use this opportunity to further the science for everybody in the world. Yeah? And that's what was done from these mission science. So there was a lot of lunar surface geological studies, a lot of sample collections from which we are still getting samples and working on them. There were a lot of experiments that were actually laid on the surface and left there. Some of them are still working. Laser retroreflectors were actually left on the moon. They are still actually returning data. Yeah? So lots of science was done, and you can see how busy the astronauts were. Either they lost the direction because they didn't know which way they were going, or they were actually walking around and setting up a lot of experiments on the surface of the moon. And you can see that there was some coring that was being done. You can even see the first electric car. You know, we are all talking about electric car today. Well, 55 years ago, people were driving electric car on the moon. Yeah? So what happened? So clearly, something didn't go quite right, and electric car didn't pick up because it was very expensive to sell it. The petrol and diesel were much easier to sell. Now we are back to electric cars, so 50 years ago. Sometimes these things come and go in fashion. For me, the most important thing was the lunar sample collection, and in this case, even more important because these astronauts, they actually logged everything from where they got the sample, what type of sample they collected, how they collected it. This is really, really important for science. One of the things they did collect was on Apollo 17. You can see a bit of, moon is very much gray and white, more or less, everywhere. But some places it does appear a bit orangish. And this was an astronaut is stumbling upon this accidentally. Yeah? Now, Some argue that this is an advantage of having humans in the chain. You make a serendipitous discovery. Yeah? A rover could have also made it. Maybe it would have taken longer time, who knows. But in this case, a human eye just spotted something unusual and went to collect those material. And it was brought back on Earth. It turned out to be orange-colored volcanic glass. Now, some of you who might have done geology would know that volcanic glass usually forms through explosive eruptions around volcanoes. And it is explosive because it is powered by volatiles. When we are talking about volatiles, now we are talking about volatiles such as carbon dioxide, water vapor, and other types of gases. Moon was considered completely dead object. It was considered completely anhydrous. The discovery of these glasses actually suggested that actually that was not quite true, at least not underneath these areas where these glasses were derived from, right? So a lot of work went on into studying the orange glasses, and it was these glasses which were reanalyzed in early 2000s that led to the discovery of water in lunar samples by a seminal paper by Saal et al. In 2008. And it was around that time that I was actually just getting into my serious bit of academic career. And I happened to be having similar samples where I had access to instruments and I was actually doing research, and I contributed to discovery. And then since then, I have been busy actually reanalyzing some of these samples myself. Yes?
Are there any other morphological features on the moon now that we see that can indicate volcanic activity in the past?
In the past? Yes, so there are lots of volcanic constructs. So maybe I should have mentioned this. See, because during 1960s, everybody was in a rush to get to the moon. So things were not done in a systematic manner. Now we are doing things in a systematic manner in the sense that you first send an orbiter. You collect the global scale maps. You collect the global scale data. You then find areas of interest, and you say, I want to explore. None of that. There's no time, right? So at that time, they just were interested in looking at areas that were easy to land, safe to land, equatorial region, near side, go there, come back, job done. Afterwards, in the next 20, 30 years, when the global scale maps were derived from subsequent orbiters, it turned out that all of those Apollo landing sites were relatively anomalous, quite anomalous geochemically. And that's why our understanding of the moon's geological history is rather incomplete if we just go by the Apollo samples, right? This is where meteorites come in, so I will tell you a little bit more about that. But going back to construct these new global scale remote sensing data set are now revealing a rich variety of landforms that seem to suggest that actually volcanism on the moon has happened throughout its geological history. Of course, the volume has been different, but now there are domes which are considered to be rich in silica. So like on Earth, we see rhyolitic dome. There are domes of granitic composition which are now being targeted for future sample return. There are areas where it looks like as if it's frothy lava. These are very strange features that could have formed in the last 100 million years. Now we say that moon has been dead since at least 3 billion years. And now here suddenly you are saying that there may be volcanism happening in the last 100 million years. I mean, that would be just the paradigm shift. But you need to actually visit those places and either do in situ measurements or collect the samples to bring back. And like that, there are many other features suggesting, from morphological point of view, that there is magmatic activity. These are just two beautiful so-called selfie from the Chang'e 5 and 6. Again, I had an opportunity to be involved in some of the research on Chang'e 5 samples through my collaboration with our Chinese counterparts. And right now, I'm actually waiting for some allocation of Chang'e 5 samples. I have submitted my application and waiting for the outcome. So hopefully one day, I can even analyze those samples in our lab. And same, I hope, for the Chang'e 6. But initially, what happens that when you do your sample return, you set a time scale. And you say for 6 months or a year or a 2 year, only people or researchers from that particular country or who has a previous arrangement will have access. And after 2 years, the sample access will be open to the rest of the world. So these are rules that are actually set by different countries, different space agencies from time to time in consultation with their communities. And I'm sure something similar will be done for Chandrayaan 4. So the title had water on the moon, and here we go. So it's not just the samples from which water has been detected, it's almost coincidental. So Chandrayaan 1 also was launched in 2009? 9, yeah. And 8, yeah. And it has several instruments, several payloads that actually were geared to detect the presence of water or signature of hydrogen, because water is nothing but hydrogen or hydrogen combined with oxygen. So either you are detecting hydrogen, or you can detect OH, or you can detect H2O. Any of those three forms would actually lead you to the presence of water in that sense. So when I say water, I mean something that contains hydrogen, essentially, is what I mean here. The Chandrayaan 1 payload called M-Cube, it actually suggested that there may be some form of hydration feature, particularly the enhanced feature towards the polar regions of the moon. So these blue colors actually correspond to those features where hydrogen is expected to be present in higher abundance. Later missions, the LRO, the Lunar Reconnaissance Orbiter, had other payload instrument that also indirectly suggested that there are these permanently shaded regions in these craters where you could even have a pure water ice. Now, if that's true, that will be a game changer. Nobody ever expected presence of water ice on the moon. And still today, nobody has actually directly touched water ice on the moon. So keep that in mind. So we should remain skeptical. We are all scientists. We are going by the data. So far, whatever data we have, it seems to suggest that there is an increased chance or possibility of finding water ice in these permanently shaded regions in lunar polar regions. But these polar areas, they have temperatures which can be as low as 50 Kelvin. Yeah? Extremely low. Some of the coldest places in the entire solar system. And some of you who are actually experimental physicists and all might find that it may be your heaven for doing experiments. You can think about doing some experiments. I know next week there will be a workshop on astronomy from the moon. Why? Because the far side is actually shielded from any radio interference from the Earth. So you could do a lot of radio astronomy from the far side of the moon. So I'm sure you will all be attending that workshop to learn more about it. So what you can find is, if you get to the moon, you can actually find your area of interest. And some people might be interested in doing the measurement on the sample themselves. Some could be setting up experiments on the lunar surface in these cold places, and some may be doing something else. So the moon provides opportunities for all. The thing is that there is a possibility that this water that is present on the moon is not just present in one form. And not only that, it may not have just one source. And to me, that is more exciting. Because if all the water is just from one source, then job done. You have solved all the problem. Yeah? But if you find that actually there is some water at the lunar pole, some of it is water ice, could have been from a different source, but then these hydration features, which are not in permanently shaded regions, could be formed through a different source. And here solar wind could be playing a role, because solar wind is nothing but charged hydrogen ions, and those hydrogen particles get directly implanted into the surfaces, onto the top surfaces of lunar soil, where they stick with dangling oxygen atoms. And once they connect themselves to oxygen atom, they form OH. Yeah? So you just produced water. The question is, how much water can be produced by that process, and is it renewable? So tomorrow, if you go and actually collect that water, somehow harvest that water, how long will it take before it gets replenished? Which is important from a resource point of view. So there is a lot of work that needs to be done. And then thirdly, the water that is present in the minerals inside the rock, the one that I have been looking at, it has to be present throughout the moon inside. So the question is, how much of it is there inside the moon? Yeah? So you need to be a detective to use the rocks at the surface to actually learn its history right from its beginning in the lunar interior, maybe 100 kilometer deep, 500 kilometer deep, depending on the sample that you are looking at. The one thing we do know that after those remote sensing indications that there are the water ice in permanently shaded craters, NASA ran an experiment by impacting a spent rocket stage in one of these PSRs, or in one of these craters called Cabeus crater. And it did reveal that there was about 5 to 8% water present. So not 100% water, but remember that it is actually impacting a large area, and it is then lifting a lot of plume in that there was a little bit of water. So you can't be striking gold in your first attempt, but at least we are moving in the right direction. There is at least some indication that there is water ice. After that, now some of the Artemis landing sites are being proposed nearby where the Cabeus crater was impacted, yeah? Because now there is an increased chance of finding water. So that's how you proceed incrementally. And I hope that similar approach would be utilized for Chandrayaan-4, because having landed Chandrayaan-3 successfully, now the team in India has a much better information about the regional geology, local geology, the expertise in landing successfully on the moon, that they should exploit that for the next phase of missions. So this is not for you, but this is mostly for non-Indian audience, because I normally go and actually sing all the praises about how wonderful achievement it was for India to land successfully and return so much of data in relatively short time, and share that with the rest of the world. Because what happens that majority of the time, if you don't share it more widely, especially through some of the non-scientific channels like press, media, etc., the rest of the world also needs to know your accomplishment. Yeah? Otherwise, you don't get the credit that you deserve. So I will just skip through this one, because I'm sure you have seen this many, many times, being more from India. But next phase of lunar exploration is going to be some competition, but I hope some collaboration too. Right? And at least there is intention. The intention is to get countries signing up to an accord or an agreement which is termed Artemis. And Artemis was the twin sister of Apollo. So no wonder that the next phase of lunar mission is called Artemis. US is leading the charge, and as of now, more than 25 countries, I don't have the exact number, but every other month, another country signs the accord. More importantly, India has signed this accord, so hopefully there will be some partnership, and of course there will be competition, and it is good. You need to have healthy competition to make progress, but at the same time there must be areas of overlap where cooperation can be had. From my point of view, for those of you who are there, and many of you are much younger than I am, that your future is going to be leading that human-robotic partnership. You cannot escape that. It's not going to be just human, and it's not going to be just robotic, at least not just yet. So it is going to be human-robotic partnership. That means that there is a huge opportunity for those who are of technical bent to come up with lots of new innovative ways of coming up with the new robotic technologies using AI and all of that to progress exploration. Yeah? And of course, I already mentioned the international cooperation, and as you know, also in India, the private sector is being encouraged to take up exploration of space, at least near-Earth space to begin with, before you delve deeper. And in the US, every other day there is news that SpaceX is testing this rocket, that rocket, and SpaceX actually has been contracted to land the next crew in the Artemis program. And other companies are also at play, so Blue Origin is there, and many other. The other thing that's going to happen that's already in progress is it's not just about landing on the moon in one go from the Earth, but go part way and use a platform which is being developed called Lunar Gateway. The concept is slightly similar, but not quite the same as the International Space Station. But the idea is that there are a lot of things that you can do with humans in orbit around the moon in something which is called Lunar Gateway for running, controlling experiments that are taking place on the moon. And also you could use this as a staging post if humans wanted to venture beyond the moon towards Mars, then come back at Gateway before going up, rather than returning all the way to Earth, because it's very expensive to leave the Earth. And again, when you come back, it becomes not only risky that you do too many times Earth return, but also expensive because you need to go back again. So this is also being developed. So right now, exploration of the moon is happening in a bit more systematic and coordinated manner than was the case 50 years ago. So if somebody asks you a question, we have been there, done that, why bother? This is why we bother. Because now it is being done with a different filter, and the benefits of what is being done, I think, is going to be far greater than what it did at that time. Arguably inspiring, half of the world was the biggest achievement of the Apollo program. But right now we are talking about these things actually contributing massively towards the economic development of many upcoming countries. Yeah? This is the main achievement. So coming to the lunar resources, I said to you that we need to be responsible citizen. We need to be sustainable, even on Earth. Resources are depleting, and every single day we are finding that actually we have less than what we thought, and we have to economize, and we have to be more efficient, etc. Same applies to the moon. So why not, while doing science, you also do research to progress some of those topics. So on the moon, the biggest resource that you have is the lunar regolith, or the top layer that is present on the lunar surface. You can call it soil. Technically, it is called a regolith because it's a mixture of small particles and big rocks. And it's not quite the same soil as we have here on Earth because it doesn't have any organic matter. So it's not appropriate to call it a soil, and soil scientifically is only reserved for material that is less than 1 millimeter in size. So we call it regolith. Lunar regolith is our treasure trove. So what is lunar regolith? Lunar regolith in composition is more or less same as any material here on Earth. How did our ancestors survive? You can go to many places. 2 days ago, I was doing field work in Kutch, and I visited the site Dholavira, where they have found the remains from the Harappan civilization. At that time, people were actually utilizing stones, and they were carving stones. The iron was not yet, discovered. So how were they cutting those stones and actually using them as bricks to make their houses? They didn't have cement mortar that we have today, but they used food waste as a cement. And it was just amazing to learn some of those things, what people were doing 5,000 years ago. That is what is called in situ resource utilization. Yeah? The same thing we will have to do on the moon is to do more with less. And for that, everything starts with the regolith. If you look at the composition of the regolith, another interesting thing that we often don't appreciate is half of it is oxygen. And as humans, what do we need to survive? Oxygen and water. And you've got the source of oxygen. Half of the planet is oxygen. But there is no free oxygen. Like here on Earth, we have got free oxygen, so we don't worry about it. But on the moon, that oxygen has to be extracted from where it is locked. And it is locked inside these regoliths. So there are a lot of experiments that are being done right now to actually extract oxygen from the moon. Now, because it is half, as soon as you've extracted your full oxygen from lunar sample, you have already reduced your waste by 50%, if there is anything called waste. So you need to go with a zero waste approach. You're not going to waste a single thing. Take out your oxygen, you're left with 50% of the material. You now extract metals or elements that are of interest from that 50% remaining material. Whatever is left after that, you're still not going to throw it and make a heap, which is what we do when we do mining. So, we all use copper, zinc, and everything else in our mobile phones. And for 1 gram of copper today, you are actually throwing away 1,000 tons of waste. Mining company is doing that, and what is being done is simply creating a waste heap. On the moon, you will not do that. You have no choice. After you've taken out those elements, you will use the residual material to build your habitat. How? By using 3D printing. Now go figure. It's your challenge. It's your generation's challenge to figure that out. I'm just giving you ideas. And I'm starting to do some experiment. I can show you the way. But all of us have to put together our brains and say, how can we come up with new solutions, new technological innovations that will minimize the waste and maximize the utilization of the material that is out there. And don't stay just on the moon. My challenge to you would be, if you do that for the moon, you will find application on Earth. And then the next question you will ask, then if you can do it on Earth, why don't you do it on Earth? Yeah, because we are lazy. We don't think that way. Unless you are challenged, you don't come up with a solution. On the moon, you are challenged, you are coming up with a solution, and they say, I can do that on the Earth too. Yeah? But we don't do it straight away. So this is, again, something which I'm very, very passionate about. And when I talk to especially school kids, and I do lots of workshops and talks, I try to tell them that you don't have to be scientists. You don't have to study only maths or chemistry or physics. Yeah? If your interest is in art, it's fine. You have to use your creativity and imagination to come up with new solutions, right? And you suddenly what you do is that you increase your workforce from a few to thousands and maybe hundreds of thousands. Yeah? So we got to bring everybody into the game and utilize and harness their potential. But coming back to the lunar dust, it's also considered a liability because it's very fine and it's very sharp. It has got grains which are very, very angular, and moon has no atmosphere. So therefore, the dust, once it is lofted, it can easily actually stay up there for some considerable time and then get into your machinery, and it can get into your space suit. And that's what created problems during the Apollo days. So it is considered a liability. But we can also convert it into an asset. So the question is lunar dust going to remain a liability, or can it be actually converted into an asset? Yeah? So just give you something closer to home. So this is my workplace. So that's my office. And these are some of the pictures from our laboratory. Some of the instruments, they are custom made, so you cannot buy them from anywhere. So we build them in the laboratories. And because we build these big instruments in the laboratories, this particular instrument, that's my colleague Sasha Warsharsky. He is Russian by origin. This is another great thing, is that in our lab, we have people who are from all over the world. We don't care where somebody is from. As long as we all combine our expertise to address a scientific problem is what we are just concerned about. Sasha has been there for 40 years at the Open University, and he has built this world's only instrument that can analyze any sample, in this case lunar sample, for its carbon, nitrogen, noble gases, for how much it is and what's their isotopic composition in one go. A facility that is not available anywhere in the world. Right? This is the machine that I would like to apply to analysis of Chang'e 5 and Chang'e 6 and Chandrayaan 4 and whatever else comes down the road, because that will add new information to what else is there. And then we have got some off-the-shelf, very high-end machines. This is a machine called NanoSims. It's very expensive in today's money. It's about 100 crore. It's one of its type in the UK, dedicated to planetary science research. And I happen to be running that facility now. That is the machine that we use to actually detect presence of water in lunar samples in the Apollo rocks. Yeah? But these machines are extremely complex, and they require a huge amount of human power to maintain them and to make sure that they run 24/7, 365 days a year, not a single day downtime. We cannot afford it. Yeah? But they are allowing us to do type of research that is bringing new discoveries and allowing us to remain at the forefront. This is not the only one in the world. There are 60 of them in the world, and the majority of them now are in China, by the way. And China has been buying these left, right, and center. It takes 4 to 5 years to deliver this machine from the day you order. So in India, it should be ordered now. Yeah? So that when Chandrayaan 4 comes back, it's there. Its previous version is already there at PRL in Ahmedabad, but it's about 20 years old, so it needs to be upgraded, to be replaced. So at least you have a machine here, but I think in 5 years' time, you will need the newest generation. And some other things are slightly basic instruments. I say these are still not so inexpensive, but they are not as expensive as that. They are secondary electron microscopes. And they are the workhorses for sample science community, because before you spend a lot of time and effort, you want to know the basic characteristics of your samples. So this is the kind of thing that you will need here, right next to ISRO when the samples are back. The first time you do your characterization, you will need one of these type of machines to do the initial characterization. So again, there are techniques and facilities which are there for a number of purposes depending upon what your objective is. As I mentioned to you, I was fortunate to be involved in some of this work and make a small contribution. So this was a paper led by my PhD student, Jessica Barnes, who is now a world leader in her own right. She is now an assistant professor at University of Arizona, and during her PhD, she used that machine, NanoSims, to do a lot of measurement in these lunar samples, and then do a bit of modeling to come up with its source. And our work at that time suggested that the majority of water inside the moon was of asteroidal origin. So asteroids essentially supplied the water that is present in the moon, and by extension to the Earth, because the Earth-Moon is one system and it has a shared history. We want to go back to the moon now, so we do work in the laboratory, which then informs the planning for various missions. In this case, I've been working with the European Space Agency for a mission called Prospect that was going to be done in partnership with Russia, Roscosmos. Unfortunately, because of the Russia-Ukraine war, Europe decided to cut its ties with Russia, and now this particular package is going to go on a NASA CLIPS mission, which is a commercial lunar payload services program, where a private company is going to provide the lander, and we as scientific community simply buy a ride by flying our payload. And so our package has been selected by European Space Agency, and there is an agreement with NASA that it will fly on a CLIPS mission in a few years' time. And other commercial leaders are coming in fray. Intuitive Machine is the only commercial company so far that has actually successfully landed in somewhat soft landing manner, not entirely successful, but more or less successful. So they seem to be leading the pack from commercial companies' point of view. I mentioned to you about habitats, because when humans are going to spend long periods of time at the lunar surface, they need to protect themselves from cosmic radiation, because the moon does not have a magnetic field, at least not today, and it doesn't have any atmosphere. So its surface is constantly being bombarded by micrometeorites, by cosmic radiation. Astronauts need to protect themselves if they are going to stay there for extended periods of time, which means you need habitats. Either you build the habitats or you find natural habitats. So earlier this summer, I went on a short trip to southern Italy in a place called Calabria, which is near the island of Sicily. And whenever I go somewhere, I like to explore the hidden places, because everybody goes to Rome and wants to see where the Colosseum is. But if you go to some far-off place, you will always be amazed. In Calabria, what I found, there was a village called Zungri. And the entire village is preserved, where people were living in carved stones. Nothing else. Yeah, it's a cliff face, and you go down the steps, and on one side it's all carved holes. You go inside, and many hundreds or maybe 1,000 years ago, people were actually living in those caves without any amenities around the world. Yeah, that's a great place to be inspired about, that how you can do with so little. So likewise, that just reminded me that on the moon, you have these lava channels, which are called lava tubes, which can be a natural habitat places for astronauts to explore and also to find shelter. Yeah? And indeed, there was a paper that was published earlier this year where our Italian colleagues actually discovered that there is a skylight, basically a hole in a lava tube that opens to the space. And then through some of the radar measurement, they actually confirmed that it continues beyond that hole, which means that this could be a place that could be used for exploring the future possibilities of sending initially robots and hopefully later on humans to do it further. In the meantime, we should continue with our work in constructing, for a better word, bricks from which you will construct your own habitat. And one of the research projects that I have been involved with for the last 10 years is using the microwaves, the same microwaves that we all use in our kitchen to warm our tea and coffee and the food and whatnot. Same microwave, it has just been upgraded to an industrial sort of standard microwave system. And what you are seeing here is a simulant material mimicking lunar soil that has been put under the microwave for 15 minutes, run at 1,000 watt, and you can see that it has already melted. It's as if you're looking down a volcano. It's more than 1,500 degrees Celsius in 15 minutes at 1,000 watt microwave. And our ultimate idea is to actually melt the lunar regolith, because there is no free water, and any water that you extract from the lunar material, you better use it for human consumption before you use it for construction. Yeah? So if you can actually construct your habitat, your bricks, without the need for cement and water, you are actually saving your resource for water resource for other use, whereas you are utilizing the regolith directly, converting, melting it, and later on you can do your 3D printing. So that part we haven't yet achieved, but we would like to achieve that. This is where I need your help, and you all can actually, give your feedback and see how this can be taken forward, or you can go and suggest that to ISRO and work with them on a project looking at this possibility. But the ultimate idea is, can you use something like microwave as a heat source to process the lunar regolith for eventually constructing or manufacturing, not just bricks in this case, so that you can build a shelter, something like that. Yeah? This is just one example, and the options are unlimited. And from time to time, of course, BBC gets interested, so they come to our lab, and then they come up with titles that will capture people's like, the Open University scientists are crazy. They are actually extracting the lunar dust for water, which is good, which gives our work a bit more visibility and the public a better understanding of the research that is taking place. I mentioned to you earlier about not just doing stuff for the moon. I'm not just doing it for the esoteric reason. I'm not just doing it for scientific reason. I'm very much aware that we are all in a very vulnerable position. The climate change is happening, and we need to find solutions here on Earth. Now, one day I was talking to my postdoc, Rich Windmill, who is now working for a company in Wales, and I said, Rich, why consider the lunar regolith as traditional mine waste? If we are trying to actually convert the lunar regolith into something meaningful, why don't we go and look at all the abundant mine waste that is there all over, especially in the UK, because UK has been so advanced in mining, hundreds of years ago. They are the one who were mining copper. They are the one who were mining lead, zinc, tin, all of that. And there are heaps of this material all over UK, contaminating the landscape. Being a risk, because if there is a huge, heavy rainfall, even 2 days ago, I saw in the news that there was a big coal heap that actually became loose in heavy water, and it created a lot of hassle. Can you imagine that if you actually find a way of remediating this mine waste? 400 years ago, our ancestors didn't know that when they were mining for copper, there were other elements also present in the same rock. I know now, because I'm a geologist. I know when copper goes, other elements have similar geochemical affinity. They also follow copper. But our ancestors had no idea what else they needed from copper. They just wanted copper. So this is dig everything. If copper isn't there, throw it. Now in your mobile phone, you need all those rare elements that are all thrown there. Work is already done for you. You don't need to dig. Yeah? All you need to do is to apply your technology to extract those metals, right? So I started a new project called Space Technology for Mine Waste Remediation. And in this case, what you are seeing is same microwave technology being applied for doing that. So this is quite a side project. It's progressing slowly because I have only that much of capacity, and there are so many ideas that can be done. But look how beautiful this landscape looks in a way. Almost looks like you are sitting on Mars. Yeah. So again, field work, analog environment for doing experiment is also presented there. So again, you can use something which traditionally considered waste into meaningful resource, more than one sense or the other. Sorry.
The bottom one, is it a carbonaceous matter or a cavity?
Here? Yeah. So these are holes.
A cavity.
cavity, yeah, where the volatiles have escaped, yeah, during the microwaving. Yeah, I'll skip this, but this is just to show that there is a circularity in everything. You can start with something and you can end there, and you need things in a circular manner if you want to be sustainable. Yeah, so you start with something where traditionally you use this part of pizza and the rest is thrown away, but now we are going to use the whole. If you're on Earth, you will follow one set of process. If you're on the moon, you will follow other set of process because your needs are different. And everything is tied to economy. If somebody is willing to pay you 1,000 rupees per liter for petrol compared to somebody who's only going to pay you 100, of course you will go where the 1,000 rupees is buying the petrol. So it's all economy at the end of the day. I didn't stop there. I said, okay, humans go there, build the habitat and everything else. They also need to grow their food, right? And I grow my own food a little bit in my own house. Every year during the summer, 6 months in the UK, I get the opportunity. I grow my corn, I grow my cucumber, I get tomatoes, I get chilies, you name it. Just sufficient for us because I want to grow and be close to the earth. I took the same approach and say, okay, what would it take to grow things on the moon, right? So there was an eruption on an island in Canaries called La Palma Island, 2021 September, big eruption. And that island was quite popular with tourists. Oh, big disaster. You know, tourism industry came to a standstill. One of my colleagues happened to be there, geologist, collected that volcanic ash, brought it back and said, Mahesh, I've got the freshest material from inside the earth. I said, fantastic, Alan. What can we do with it? He said, let's use this as an analog of lunar volcanic ash. Yeah? And let's mix it with a little bit of compost. 100% ash to 100% compost and things in between. And I planted some seeds, and this is in my back garden. I just sat down with him and I planted some seeds of salad leaf called rocket. I don't know if you've heard about that or not, rocket salad. And I called the project Green Rockets for the Moon. Do you see the pun? Green rockets for the moon. So you are not only green in one sense, more than one sense, right? And surprisingly, we grew rockets in things that had 75% of the ash with 25% compost. Nothing grew in 100% ash. We didn't expect to. But the point is, you don't need to carry 100% compost to grow what you need. I've just reduced your compost use significantly if you can grow something. So it's just a concept, it's an idea, right? I then actually preserved all those leaves into my herbarium. I sent it across to Finland to my collaborators. Can you do XRF analysis in the leaves that were within more compost versus less compost? Because I want to see what is the elemental uptake. Yeah? Is one taking more or the other? Because I need to understand that. Again, I would like somebody else to take this project with full throttle. You know, we've done that, it's there, but it's so fascinating and it's so exciting. You can do so much more. And I don't know, here you may not know him, but he is a celebrity in the UK. He is a physicist, by the way, yeah, who went to work for BBC and became almost a comedian. His name is Dara O'Brien. Yeah? He's from Ireland. So he was making a program with, I think this is Channel 5. I think this is Channel 5. Yeah, Channel 5. They called me and said they want to come to my lab and do some filming, and they will come with Dara O'Brien. Now, Open University is in a place called Milton Keynes, which actually I'm sure none of you have heard of, right? And so Dara O'Brien, and the same is in England, because most of the cities and towns are so old that every time you talk about England, they think of 1,000-year-old. So it's a laughing matter, like say Milton Keynes. Yeah, who goes to Milton Keynes? It's only 50 years old, you know. So he goes into this documentary. Of all the places I'm going to, Milton Keynes. You know? It's like, where else would you go if you're looking for future? That's how Milton Keynes was conceived. It is a planned city, but it doesn't have the same type of cultural appeal as the rest of the city. But here, it makes so much sense that the newest city in the UK is actually at the forefront of where things are going. So that was fun, and it was 2-series program, and half of the second one was all based on our work at the OU. So it was good to work with him and get our work again out through these people who are the best ambassadors, you know, to the public. Then chemistry world came to me and said, okay, can you say something about why there is a race and all that? And they chose to make this cartoon after talking to me. I didn't do anything, but you see, they put a spade there on the moon and say, okay, a race to build the moon, base on the moon. Of course, this was on the back of a paper that Ian Crawford and other colleagues and I wrote. How will you manage, how should we manage activities at lunar poles? Because tomorrow, if everybody wants to go and actually start extracting that water ice, if it is indeed present there at lunar pole, it could become a bit of a wild, wild west situation, right? Again, we are going to destroy the environment, we are going to destroy and replete the resources, etc. So we put out a position paper saying, perhaps we should focus our activity more in the south polar region of the moon, initially keeping North Pole preserved for posterity, for our future generation. These type of discussions are starting to happen in the community. They need to happen before actually it's too late. Okay? So as a scientist, you don't just do science, you don't just do education, you also need to inform the policymakers, you also need to make suggestions of how things should be managed. So it's a whole package. And of course, in my favorite picture that, on the right-hand side, you see from the dry run of the Artemis 1, where it has gone way beyond any other mission has gone that is human rated. And it took that picture where you can see the Earth in the background and the far side of the moon in the foreground of the Earth. Amazing, amazing picture. And these are the, hopefully, some of them, if not all of them, will be the next humans who will be setting foot on the moon. And certainly, these 4 should be going on a round trip sometime soon. And I'm very proud of my recent PhD student who has just moved to Canada, who is now actually training these astronauts in field geology. So once again, working on lunar samples, and she worked on lunar meteorites, and now ending up actually training those people who will be the next one going to the moon. And in the UK, we have 3 new astronauts who have been selected by ESA, and maybe, and actually especially John McFall, he has a disability. So he is right now training as a first para-astronaut and see whether people with certain disabilities can also go in space or not. So this is yet another thing that in our society, we often neglect and ignore a large number of people who actually have a tremendous potential to contribute to what we are trying to do. So all in all, I think in the last 50 years, if we have learned anything, or at least that's my observation, that if anything has been learned, it is to respect and give credit to everyone and be inclusive in your approach. And I think you probably would agree with that. And nothing beats this, because when you talk to the young people, and when you hear my colleague is just showing a lunar globe to this kid, and she's getting excited and ask many questions, and then now you can have, of course, you can walk on the moon with the virtual reality headset. You can have that experience. Or you can look at some of these rocks. So this was an exhibition I put together on behalf of the UK community at the Royal Society on the 50th anniversary of the Apollo 11 landing in 2019. We had 6,000 people who came in over 4 or 5 days. It was very tiring, but every single second was worth it. And of course, we need to live on the moon or explore the moon, but we really need to be thriving here on Earth. And I think that would be it. And I love this picture. This was after Chandrayaan 3 landing. Nature published this picture, and see this, the young explorer, yeah? And the moment I saw it, I said, this is going to be in my slides, because this just shows that the opportunities are unlimited. And when you're that young and that innocent, nobody is going to tell you that that is impossible. Everything is possible. Thank you very much. So
Thanks.
happy to have questions.
Yeah, thanks for a great talk. I think we are open to questions.
Hi, Mahesh. Thanks for the wonderful talk and inspiring all of us. I had a question regarding the volcanic glass beads that you mentioned. In regards to Chang'e 5, I think there was some recent paper where they found 3 glass beads in a 120 and dated them to 120 million years ago as a very young volcanic activity potentially. Can you share something about that and contextualize it maybe?
Those were impact glasses.
Yes, I'm not sure actually, that's why I'm asking.
Yeah, so I think those, I have to double check, but I thought that those were all impact glasses, and what they were telling us that those type of glasses were forming until very recently, unless I'm mistaken. Yeah, but let me check and get back to you, because that is really important. Yeah, but the truth is that more geochronology or radiometric dating is being done, more ages are coming forward. So the Chang'e 6 papers that were published last week, they reported 2 sets of ages that were unexpected from these samples. One very old at 4.2 billion year, and the other at 2.8, for which we didn't have any lunar samples dated in our record. Yeah? So that way they gave us 2 extra points on that cratering curve that I told you before that is used for calibrating the ages of other surfaces. Yeah? So anytime you bring samples back, the first thing you want to know, how old is it? Yeah? And if it is actually volcanic sample, as it might be, Jatin, that you said, but it's now, right now it's evading me, so I'm not 100% sure. With volcanic samples, what it is telling you is the time at which it came from inside of the moon onto the surface. So that is then added extra significance. Whereas if something is dating the impact age, it is simply at that time that it went through a high temperature phase where its clock was reset. Could have been there for a long period of time, but after the impact, the entire radiometric clock was reset and it started ticking again. So that's the last period that it was done. But timing is very, very crucial. And then you go on to connect your chemical compositions of that material and the isotopic measurement with the timing to get the fuller picture.
Basalt in lunar sample. So how are they different from igneous basalt of Deccan lava, Deccan flood basalt? Chemically, are they same or are they different? And mostly the samples in lunar samples, they are homogeneous, I reckon. It's not heterogeneous, is that right? Or how it is different from Deccan flood basalt to the lunar basalt rocks?
Sure.
Chemically, geochemically.
Yeah, so geochemically, first order, they are very similar. They are basalt, like Deccan basalt. So they are magnesium, iron, calcium, silicates. That's all they have. So olivine, pyroxene, plagioclase. These are the 3 main minerals that are there in Deccan basalts, lunar basalts. Now, what is now different in lunar basalt is the proportion of some of these minerals compared to the Deccan, and especially in lunar basalts, particularly the abundance of mineral ilmenite, which is an iron titanium oxide. Now, on Earth, we don't find that much of ilmenite in Deccan basalt and other similar terrestrial basalt samples. On the moon, it turns out there is a huge range in the abundance of ilmenite, which could vary from almost nothing, just like our terrestrial counterparts, all the way to 15 to 20% in the rock. That's a huge amount of ilmenite, and that's where people started scratching their head and say, how could you produce a magma so rich in ilmenite? And these are the basalts which were termed high titanium basalts. So on the moon, the basalts are classified based on their titanium content, which is basically an indirect proxy for how much ilmenite is there, because that is the main mineral for titanium. Very low titanium, high titanium, and there is one more called intermediate titanium, which we didn't sample during the Apollo days, but they are now appearing in meteorite record. And I didn't really talk much about meteorite because the talk would have been even longer, but meteorites are those rocks that are discovered on Earth, but they were liberated from the moon by an impact, right? And the fact that those impacts on the moon could have happened anywhere, you are not now restricted by only sampling those areas where Apollo landings happened. So you could have a meteorite coming from far side, you could have a meteorite coming from the South Pole, anywhere. So they are actually covering a large spectrum of chemical composition. So as a first order, not a huge difference, but at detail level, there is a difference. And those chemical differences are linked with the origin of the moon itself. Because 4.5 billion years ago, the theory goes that the only way we can reconcile all of our observations if Earth had already formed and there was a huge impact with that growing Earth from which the material was ejected, forming the moon. Therefore, the Earth and moon have so many geochemical similarities. No two other bodies in the solar system has the type of geochemical similarities that our Earth and the moon have, right? And after the moon started forming, it went through what is known as a magma ocean phase, where actually it started cooling layer by layer, and there was a stratification. So at the very top, something that was less dense, like plagioclase, floated at the top, and that's what forms those light regions that you saw. It's known as highlands or anorthosites, as it is called. And inside, there was a layer that became very rich in titanium, because titanium is known as incompatible elements. It quite doesn't fit into mineral structure, so it tries to remain in the liquid while other minerals are forming. But eventually, it has to go into a mineral. And when it is sufficiently enriched, it forms a mineral ilmenite, right? So the theory is that it is those layers, ilmenite-rich layers, that then became involved in the subsequent generation of volcanic rocks. That's why you see such a huge variation in titanium. So those are the reasons, but then there are some other differences. But in general, I think that that's another thing that geoscience students don't appreciate. That actually they are best equipped to study the moon. Because rocks on the moon are no different than rocks on the Earth, right? And somehow there is an inhibition that as soon as they work on the moon, it becomes planetary science. Earth is a planet too. You are already a planetary scientist, huh? So today, moon, tomorrow, Mars. So I would also encourage that if you know, or if you're not already geoscientists, but if you know geosciences, please encourage them to start exploring, because next 10, 20 years, India is going to need a lot more sample scientists. And we need to start training them now, if we haven't already done so.
May I add one more suggestion?
Please.
See, the Deccan basalt has a lot of zeolites, okay, minerals, which is used for catalyst industry of oil and all. Moon basalt doesn't, till today, there's no report on any zeolite from moon. That's a major thing. Exactly. That is there. That's a major difference between both. Apart from what he said, this is a major difference. No, water also plays, but there is a rare silicate called mogonite, SiO2. Silicate mogonite
Yeah.
is found on moon surface. For estimating how much water it has, they used our work, which we published in 2000 from Deccan basalt.
Yep. So the thing is that those are some of the major differences where the moon is a relatively fluid, poor body. So the amount of fluid that is available on Earth is much more, and therefore it is more heavily involved in geological processes, whereas on the moon, we still say there is water on the moon, but it's all relative. It's relatively still thousands or 4 orders of magnitude drier than the Earth. Yeah? It doesn't have that much of water. Final thing is that impacts play a big role on the moon too, in remobilizing and redistributing material, which we don't see that much here on Earth because we have such a thick atmosphere that it doesn't allow, and for good reason, you know, most of the meteorites not to come to surface. Whereas on the moon, there's no atmosphere, so these impacts are constantly gardening, churning, redistributing material, and during those impact processes, new minerals are also being formed. In fact, I was very lucky to actually discover a new mineral on the moon during my postdoc. And that mineral had never been reported before, so I even get a chance to name it. Yeah? So some of these things are similar to Earth, but the other things are completely open, and you never know what you discover. Yeah. Any other question?
Any other questions?
Yes, it's called hapkite. So I found a compound of iron silicon. Normally iron and silicon do not combine with each other because they both like to go with oxygen. So if oxygen is present, iron will go, I'm coming with you, silicon says, I'm coming with you, and they all then go together, iron, oxygen, silicon. On the moon, because the condition is so reducing that oxygen, in this case, my hypothesis was, I only know this is a new mineral, so I know for fact that iron silicon occur as a compound. The question is, how did it come about? So here I go from the real fact to interpreting how it might have happened. And the interpretation is that during an impact event, and this is by micrometeorites, the top surface of the moon was volatilized. Oxygen being the lighter element of the three, of the lightest of the three, iron, silicon, and oxygen, was preferentially lost. And because it's such an oxygen-pure environment anyway, you lose oxygen more easily, leaving behind iron and silicon that had no other way to do anything other than to combine. And that's where you form iron silicides. Professor Bruce Hapke was one of the leading scientists in the Apollo times who predicted the presence of such type of phases on the lunar surface, because he saw that in the reflectance spectroscopic data, there was an effect of a phase that was not known that was causing a change in what they were observing. So he had said that some phase like that could be present. And therefore, when I discovered that, I named it in his honor as Hapkeite.
Any other questions from the audience? If not, I had a very quick question. You at some point mentioned about the possibility of different sources of water. What kind of studies have motivated different sources?
Great question. And I wish I could have shown you many more slides. So we measure the amount of water, which means the amount of hydrogen or OH or H2O, but we also measure its isotopic composition, which is deuterium to hydrogen ratio. Now, it turns out that a lot of material in our solar system has a very specific deuterium to hydrogen ratio. So if you look at asteroids, if you look at comets, they have very different deuterium to hydrogen ratio. So the Earth has a different deuterium to hydrogen ratio. In fact, that is very similar to the majority of asteroidal material. So that way we use the amount and its isotopic composition as a means of fingerprinting where that hydrogen could have come from. If the hydrogen is coming from solar wind, its deuterium to hydrogen ratio is completely different to anything else I have said so far. It has almost no deuterium, right? So its delta D value is almost close to negative 1,000, negative 960 or something, whereas Earth, interior of the Earth is around 0. Yeah? The sun is negative 960. Comets are plus 5,000, right? So if you measure something that maps onto one of these reservoirs, you get the first hint that that's where the hydrogen might have come from, provided that hydrogen, since its delivery, has not had its isotopic composition modified. Yeah? And that's a whole can of worms I just opened, because you have what is known as spallation reactions. Cosmic ray spallation causes production of more deuterium over hydrogen in any material that is exposed to them. The moon has no atmosphere. So here, my friend, cosmic rays come in, and they change the deuterium to hydrogen ratio in the first 3 meters. So next time when the Chandrayaan is going, if it goes below 3 meters, I would be very happy to get some samples, provided it has not been churned over. It was there for 1 billion and then churned over. So there are lots of ifs and buts all the time. But you see what I mean. So you have to take care of spallation. The other thing that also happens is moon has no atmosphere, so when the volcano is erupting, the magma loses its volatile gases much more efficiently and effectively than it happens on Earth. Yeah? And when you are losing hydrogen from a magma, because deuterium is twice its mass, you lose more hydrogen compared to deuterium. So what happens is whatever is remaining has artificially high deuterium to hydrogen ratio because some of that hydrogen has been lost. So now if I'm measuring high deuterium to hydrogen in lunar sample, is it because of comets? Is it because of spallation? Is it because of degassing? Yeah? How can I take these processes into account to get this into original situation? So that we do lots of ifs and buts and all, and so far what we are seeing is that the moon has got similar delta D as the Earth, and possibly even lower than the Earth. because the Earth's deuterium to hydrogen has been modified through its geological history. And we believe that Earth is started with a much lower deuterium to hydrogen, and it has been elevated. Whereas the moon, being a one-plate planet, has not had that change. So that's where we are going, but we need more samples to actually test the hypothesis and prove that is the case.
Thanks. Any last questions? If not, then let's thank our speaker once again. And I invite Professor Reggie Philip to hand over a souvenir to our speaker. Since you have Raman connection.
Wonderful. I have something to read.
Thanks a lot, Mahesh, for the
Thank you.
talk.
Thank you. Thank you.
A small token of our appreciation. Oh, yes. Yes, yes, you are right.
Wonderful. Thank you very much. And thank you.
Yeah, thanks a lot. And we have high tea, so please join us just outside the auditorium.